Welcome back to Calculus 2. I'm Dr. Jeff Groh, and today we're going to talk more about infinite series. I'd like to begin by looking at a particular example. This example, by the way, is famous. You need to know it. Suppose I have the sum, as k goes from 1 to infinity, of 1 over k. The terms of this series are 1 over k. Before progressing, I want to recall to your memory the divergence test. The divergence test says that if the limit as k goes to infinity of a sub k is not 0, then the series diverges. The implication here is if the terms don't go to 0, there's no hope. The series will diverge. But what about the other way around? What if the terms do go to 0? What does that imply? It turns out it doesn't imply anything. There are series that have terms that go to 0 that yield infinite sums, and there are series that have terms that go to 0 that yield finite sums. So just because the terms go to 0, that tells you precisely nothing. This series is called the harmonic series. And it's famous because it demonstrates that although the terms of a series may go to 0, it might still diverge. This series, we will prove, diverges. I'd like to begin by making a graph. At k equals 1, this function has a height of 1. And in addition to that, I'm going to draw a rectangle of height 1 and of width 1. So the area of this rectangle is 1. At k equals 2, the height is 1/2. So I'm going to make a rectangle of area 1/2. Then 1/3, 1/4, and so on. So we have all of these little areas. If we add these areas up, we get the value of the sum of the harmonic series, whatever that is. Let's compare that to a function. The function is f of x equals 1 over x. This function passes through these left corners on each of these rectangles. It can be seen from the graph that the area under the curve 1 over x is less than or equal to the amount of the sum. Do you see that? The sum is the area of the rectangles added up. The integral gives you the area of the undergraph for the curve 1 over x. The area of the undergraph is below these corners on the rectangles, and hence you get a smaller total area. So, how big is this area? The integral is improper. What is an improper integral? One that does inappropriate things in social settings? Well, it's improper because one of the limits of integration is infinity. So we'll take the limit as that limit of integration goes to infinity. We have then the limit as L goes to infinity the natural log of the absolute value of x evaluated from 1 to L. That's the limit as L goes to infinity of the natural log of L minus the natural log of 1. What's the natural log of 1? Well, that's 0. The natural log curve at 1 is at a height of 0. But what does the log curve go to as L gets bigger and bigger, as L goes to infinity? And the answer is, it goes to infinity. Now keep in mind, we said that this was bigger than or equal to the sum of 1 over k. K goes from 1 to infinity. If the smaller value diverges to infinity, you see that the larger value must also diverge to infinity. Although the terms went to 0, nonetheless, they didn't go to 0 fast enough to pick up a finite sum. Instead, the sum diverged to positive infinity. Isn't it fascinating that we were able to compare a sum to an integral, and then the integral could tell us whether or not the sum was finite? There must be a way to systematize this. There must be a theorem. It's called the integral test. And it goes something like this. If f, which maps from 1 to infinity into the real numbers, is 1, non-negative, it's positive, meaning f of x is greater than 0 for all x within the domain 1 to infinity. 2, continuous. 3, decreasing. And 4, f of k equals a sub k for all k in the element that are elements of a set of natural numbers. Then both the series and the integral from 1 to infinity f of x dx both converge or both diverge. So if the integral converges, then the series converges. If the integral diverges, then the series diverges. That's the way they're going to use this theory on the examples coming up. The culture of mathematics is one of truth. We don't accept things without proof. Fortunately, the proof here is very similar to the proof that we just gave for the harmonic series. But we have to go both ways. We only proved divergence for the harmonic series. Our theorem says both converge or both diverge. So we have to prove it both ways. So let's draw a picture to see how the proof goes. We said our function f needs to be continuous, decreasing from 1 to infinity, and is positive. And what is more, it equals our series at each of these points. The way that we've set this up right now, the series will produce areas of these little rectangles that are above the area of the integral. So we get the following inequality. the integral from 1 to infinity of f of x dx is definitely less than or equal to the sum, as k goes from 1 to infinity, of a sub k. So the area represented by the series will dominate the area of the undergraph. But wait, there's more. If only we had drawn the rectangles a little differently. Again, here's f of x. From 1 to infinity we have this undergraph, but instead of drawing the rectangles to the right, let's draw them to the left. Now you can see the area of the undergraph will dominate the sum except for the first term, which we have to subtract off. What that gives us is that minus a1 plus the series will be less than or equal to the area of the undergraph. It's analyzing these two inequalities that will allow us to make the conclusion on the theorem. You can see now that if the series diverges, the first inequality on the left will imply that the integral diverges as well. The only way a series with positive terms can diverge is to blow up to plus infinity. So the series, if it has a limit that goes to plus infinity, then the integral will also have a limit that goes to plus infinity. But the second inequality tells us that if the integral has a limit that diverges to plus infinity, then so does the series. So if series diverges, then the integral diverges, and then if the integral diverges, then the series diverges. Both of those will diverge together. What about convergence? If the series converges to a finite limit, a finite sum, that proves that the integral must also, by the second inequality. But then the first inequality tells us that if the integral has a finite limit, then so must the series. So if the series converges, then the integral converges. And then if the integral converges, then the series converges. All of this is given to you by this sequence of inequalities. From these we deduce that both converge or both diverge. And that's the end of the proof. I want to give you some straightforward examples. Suppose I have the sum, as k goes from 1 to infinity, of 2k divided by k squared plus 1. Before launching into a careful analysis of this series, I'd like to teach you how to look at it intuitively. If k gets big, let's suppose k is about 1,000,000. What is 1,000,000 squared? 1,000,000 squared? Why, that's 1 trillion. 1 trillion plus 1? If you have $1 trillion and $1 falls out of your pocket, do you care? You could spend $1 million for the next 1,000,000 days, and you still wouldn't run out of money if you had $1 trillion. $1 trillion makes 1 meaningless by comparison. So, as k gets big, ignore the small stuff. Just cover it up that little 1 there and forget about it like it doesn't exist. If the 1 isn't there, then this fraction reduces to 2 divided by k. The 2 doesn't matter so much because you can factor 2's out, a common. The 2 doesn't matter much because you can factor the 2 out of the sum. That means you get 2 times the sum of just 1 over k. But 1 over k is the harmonic series. And you know the harmonic series is famous for diverging. So you suspect this series, when k gets big, should behave a lot like the harmonic series and should diverge. We will prove this using the integral test. We'll integrate from 1 to infinity 2x over x squared plus 1 dx. Do you see how we've made the replacements? Now, this looks a lot like a u sub. It's a u sub because we have the derivative of something lying around. We'll set u equal to the thing that has its derivative lying around, in which case du will be 2x dx. Notice that when x is 1, u is 2, and as x goes to infinity, u goes to infinity. We're left with 1 divided by u, and 2x dx goes away to become du. We can write this as the limit, as that upper limit of integration goes to infinity, of the natural log of L minus the natural log of 2. What does this all go to? We just saw a moment ago. The natural log tends to infinity as L goes to infinity. That says that the whole thing diverges to plus infinity. That means by the integral test, since both converge or both diverge, the original series diverges. Let's look at another example. The sum, as k goes from 1 to infinity, of 1 over k squared plus 1. This looks awfully similar to the last example. What's different is that we have a 1 in the numerator instead of a 2k. We'll use the integral test again and integrate from 1 to infinity 1 over x squared plus 1. Yes, that's the one. That's the one I wanted you to remember. This will be the limit. As L goes to infinity, we'll have arctan of L minus arctan of 1. Remember how the inverse tangent looks. It has 2 horizontal asymptotes, which is the most any function can have. But as you go to the right, as you go to infinity on the right, the curve goes to pi over 2. And the inverse tangent of 1 is pi over 4, because the tangent of pi over 4 is 1. The value that we get doesn't matter so much. What matters is that the value is finite, which means that the integral converges. That means that the series converges as well. It doesn't tell you what the series adds up to. It just tells you that whatever the sum is finite. I'm going to define a new kind of series. It's called a p-series. A p-series is a series of the form the sum, as k goes from 1 to infinity, of 1 over k to the power of p. We're not assuming that p is a natural number or even a whole number. P could be a fraction like 1/2. It could be pi, could be an irrational number. P could be some real number. The question that we have next is, are there some values of P for which a P series converges and others for which it diverges? And the answer is yes, or else I wouldn't have asked the question. We have something called the P series test. And it goes something like this. The P series converges if P is strictly greater than 1 and diverges if P is less than or equal to 1. So 1 is the dividing line. You have to be strictly larger than 1. Notice that if I have a P series, and if P is equal to 1, then it is the harmonic series, which we have already shown, diverges. That's in this case here. So in our proof, the first thing we'll note is that if P is equal to 1, the series is harmonic. And hence diverges. Let P be greater than 1. Then applying the integral test, we'll integrate from 1 to infinity 1 over x to the power p. This will be the limit as L goes to infinity. We can rewrite the integrand as x to the minus p, so that when we integrate, we'll have x to the minus p plus 1 over minus p plus 1, evaluated from 1 to L. We have then the limit as L goes to infinity. Now keep in mind, we've assumed that P is greater than 1 in this case. If P is bigger than 1, that implies negative P plus 1 is a negative number, which means we should lower this across the division symbol to make the exponent positive again. We should rewrite this as 1 over, we have negative P plus 1 on both terms. We may as well write this as 1 over L. If I take a factor of x to the power of negative P plus 1 and cross the division symbol, I'll have a power of P minus 1. And when I plug in 1, I'll just have 1. So now P minus 1 is positive, and I'm sending L to infinity. Since L goes to infinity, this whole term goes to 0. And I'm left with 1 over P minus 1, distributing this negative through the denominator. Keeping in mind P minus 1 is positive. The whole thing is finite. That means the series converges. So when P is greater than 1, the P series converges. There's still another case to consider. What happens when P is less than 1? If P is less than 1, we may still use the integral test. But in this case, if we move this over, 0 will be smaller than negative P plus 1, and hence the exponent will be positive. We'll have to rewrite this as the limit as L goes to infinity. We'll bring the negative P plus 1 out front. We'll have L to the negative P plus 1 minus 1. But now, remember, negative P plus 1 is positive, which means as L goes to infinity, this term goes to infinity. The whole thing blows up, therefore the series diverges. Now, we're done with the proof, but the implementation of the theorem is really very easy. Let me give you an example. Suppose I have the sum, as k goes from 1 to infinity, of 1 over k squared. You need to be able to identify this as a p-series, and hence use the p-series test. In this case, p is 2, which is strictly greater than 1, and therefore the series converges. I have all three parts that I want you to demonstrate on the exam. I want you to state the test, I want you to implement the test, and I want you to state the conclusion of the test. One thing I want you to note is we don't know what this sum is from this test. You probably wouldn't know that the sum adds up to pi squared over 6, but that takes a lot more theory. So we are going to content ourselves to just determining whether or not the sum is finite. As another example, suppose we have the sum as k goes from 1 to infinity of 1 over k to the power of 1/2. The square root of k is in the denominator. What happens here? Well, we can use the p-series test because this is a p-series. P is 1/2, and that is less than or equal to 1. This is the divergence condition. And therefore, the series diverges. Less than or equal to. I want you to remember that. If it's strictly greater than 1, it converges. If it's less than or equal to 1, then it diverges. Let's look at another series. The sum as k goes from 1 to infinity of the arctangent of k divided by k squared plus 1. Converge or diverge, and what method might we use to prove one way or the other? It looks like if you could replace k by x, isn't the derivative of inverse tangent equal to 1 over x squared plus 1? It looks like we have the derivative of something lying around. It looks like this is begging for us to use the u substitution method on an integral. In other words, it looks like we should use the integral test. We'll integrate from 1 to infinity arctan of x over x squared plus 1 dx. Don't get cheap with me and leave off your dx's. They're important. If we set u equal to the thing that has its derivative lying around, then du will be 1 over x squared plus 1 dx. Now, let's think about this. Technically, there's a limit that goes on here. A limit as the upper limit here goes to infinity. If I plug 1 in for x, arctan of 1 is pi over 4. As x or L goes to infinity, u goes to pi over 2. So we're getting u du. It should be clear right now. This is going to give you a finite value. Since the integral was finite, the integral converges, therefore the series converges.